tape. It's a pleasure for me to welcome you to Water Talk today and introduce Dr. K.J. Reddy, who is a research associate with the Water Research Center. Dr. Reddy has an undergraduate degree in agriculture and also a master's degree in soil chemistry, which he obtained in India, the latter in 1980, before he went to Colorado State University, where he completed his PhD in soil chemistry under Dr. Lindsay in 1986. Subsequent to finishing at CSU, he came to the University of Wyoming, first as a postdoctoral associate and now as a research associate with the Wyoming Water Research Center. He's a member of the Soil Science Society of America, and his research interests focus primarily on the accurate measurement and determination of solubility controls for various inorganic trace constituents, particularly in solid waste materials associated with various forms of fossil fuel energy production. His topic today is measurement of calcite ion activity products in soils as related to the quality of water. KJ, welcome to Water Talk.
Thanks.
Okay. Let's start with some of this. What I will do is I'll briefly explain about calcite equilibrium in soils. The whole topic is mainly on soils, but we can relate this one to other environments like surface water or groundwater systems and so on. Then show some of the results we obtained in a laboratory experiment, and then conclude some of the results we got from that experiment. Okay, let's go to the introduction. The ability to predict the pH of soil solutions is essential in order to understand the behavior of many trace elements that may present toxic problems. That means maybe they are toxic environmentally and may be essential for plant nutrition. Okay, the major control for pH in soil solutions is the carbonate system. How that one works, as water infiltrates into soils, its dissolved carbon dioxide and dissolved organic carbon concentrations increase as a result of soil microbial activities. Once you increase those two, the pH of infiltrating waters will go down. The infiltrating water, when reacts with the calcite, which is present in the soil, then calcite will try to bring up the pH of that water to around 8. This is, fundamental thing how it works, the whole carbonate system in soils. Okay. However, many natural waters, including lakes, rivers, and soil solutions, often show supersaturation. That means a non-equilibrium condition with respect to calcite. There's plenty of literature on that one, okay? There are some reasons for that supersaturation. Some of them are the most important or listed here. Number one, the inhibition of calcite precipitation process by DOC, that is dissolved organic carbon. What that means is when calcite is trying to precipitate, then dissolved organic compounds will block the crystal growth. That's why you observe calcite supersaturation. That's one of the reasons. Then second one is magnesium substitution into calcite. Sometimes magnesium will substitute into calcite structure also. Then that will give you the supersaturation. The third one, organic matter mineralization in soils. This is mainly towards soils. Organic matter will mineralize in soils. Then result of mineralization, you get CO2, then that will end up as excess bicarbonate alkalinity. Therefore, you see the calcite supersaturation. But the most important thing is the inhibition of calcite precipitation by DOC. Let's examine what we need to measure in order to examine the calcite saturation state in solutions, okay, soil solutions. Okay, in order to determine calcite saturation state, that means equilibrium in soil solution, requires accurate measurement of calcium and carbonate ion activities. Okay, often calcium activity is measured by speciating the total calcium, which was measured by ICP or AA. AA means atomic absorption and then inductively coupled plasma. Whereas the carbonate activity will be calculated from speciation of total alkalinity measured by direct titration method. We should remember those two methods, okay? That's why I underlined those two. However, these methods may overestimate calcium and carbonate activities due to dissolved organic carbon. Okay, why? When we use atomic absorption or ICP to measure calcium total, soluble calcium total, we are measuring both inorganic as well as organic complexes of calcium. You just burn everything and then measure total soluble calcium. Okay, the second method, direct titration, what you do is you take the soil solution and then titrate to different pH endpoints and measure total alkalinity. There also we are, if you have some dissolved organic compounds, they also absorb protons during the titration, so you end up with excess alkalinity. So what we have to do, okay, what happens if you overestimate calcium and carbonate activities? Eventually you end up with supersaturated values for calcite. Okay. The objectives of this research were to measure accurately calcium and carbonate activities in soil solutions and then measure the saturation state of calcite in soil solutions. I think I'll go to slides now. Okay, if you have any doubts, please ask questions, okay? Don't hesitate to interrupt me, okay? Okay, in this study, this is mainly laboratory study. Please understand that, because it has some implications when you try to apply to field conditions. So I want to emphasize that this is a laboratory study. In this study, we used 3 calcareous soils. I just number them as 1, 2, and 3. I think soil number 1 came from Fort Collins, Colorado, nearby the Fort Collins. And then soil 2 and 3 were collected near Laramie Basin here in Laramie, Wyoming. Okay, these soils, these are calcareous soils. These were air dried and passed through a mess, and then the sieved samples were used for solubility measurements and then X-ray diffraction analysis. Briefly, X-ray diffraction analysis, we found a good calcite peak in those soils. That means calcite solid phase or mineral is present in those soils. Let's go to the solubility measurements. In this, what we did, we took 25 grams of soil in duplicates, suspended in 250 ml of flask with 100 ml of distilled water. Then we bubbled. We need to fix the carbon dioxide here because that's one of the constraints we have. That's an important parameter. If you don't fix that one, somehow you have to measure CO2 accurately with the soil, which is equilibrating. So to fix that, what we did is we bubbled laboratory air through the distilled water and then the soil suspensions while they were shaking. And we reacted the samples at 25 degrees on a mechanical shaker. Then we also added 3 drops of toluene in order to suppress the microbial activity. Microbes grow in the soil suspensions if you react for a long time. Then there is some problem with microbes, so we got rid of that problem by adding toluene. Then we reacted soil solutions 1, 3, and 7 days. After that, we filtered the suspensions and then measured for pH, EC, cations, and dissolved organic carbon. Okay, this is routine chemical analysis. I don't want to spend too much time on this one, but the most important thing here to remember is calcium. Okay, we measured calcium with ICP That means it includes both organic and inorganic soluble calcium. And also we measured calcium activity with calcium electrode. What this does is it measures only inorganic calcium activity. It will avoid if you have any calcium organic complexes. So these are the two major things you should remember here. Then rest of the analysis are routine. I think most of you know. And we also measure dissolved organic carbon in those solutions with a carbon analyzer. Okay, the next one is carbonates. We measured calcium, right? Carbonates. Carbonates in soil extracts were measured by two methods. One is direct titration method, in which you titrate soil solutions to two different endpoints and then take total alkalinity. Okay, that's mentioned here. The second method is shown here. Okay, by the way, this is called CO2 gas release method, okay? What we did here is, this is organic gas. This is the second method of measuring carbonates accurately, avoiding any organic complexes or organic carbon compounds. Okay, organic gas connected to ascarite tube. The reason we connected to ascarite, to remove any traces of carbon dioxide present in that organic gas, organic tank, because we found there's plenty of CO2 in those tanks, because we are trying to measure precisely the CO2 here. So we need to be very careful. So to be a check, we put ascarite here. Then ascarite was connected to a sample chamber through peristaltic pump here. Then sample chamber was connected to a sodium hydroxide trap, okay, chamber here. And we have, this is gas outlet. In sample chamber, we inserted a burette to titrate solutions. In the sodium hydroxide chamber, we have a pH electrode connected to a pH meter to monitor the pH of solutions. And then we have a burette again to titrate the solutions. Okay, before we start anything, we just bubble argon gas, which is free of CO2, through the system a couple of minutes. Then get rid of all the CO2, whatever present in this system. Then we put 10 ml of soil solution, which was filtered from the equilibrium studies. And then we put 10 ml of sodium hydroxide plus barium chloride in this sodium hydroxide chamber. Okay? Then we disconnected here and then connected 10. Okay, gas left leg right there. Then we acidified sample here, soil solution, to pH 4 by just adding acid, right? Once you add acid, whatever carbonates you have, you destroy the carbonates and then CO2 comes out of the soil solution. Okay, that CO2 was bubbled through the sodium hydroxide here for 1 hour using this peristaltic pump. That's the main function of the peristaltic pump. Okay, after 1 hour, we titrated the solution here to pH 8.3, monitoring the pH. Okay, then we remove the samples, then we put a blank here, went through the same procedure, and then measured carbonates in the blank. So the difference between your blank and sample should give you the carbonates, okay, total carbonates as evaluated as CO2 in the sample. So here, you are not getting any organics here. That's the difference, okay? We also ran some standards here, sodium bicarbonate standards. We get excellent recoveries. We found excellent recoveries from this method. Let's see, I hope this one. See, R square is almost 1. Okay, so we got excellent recoveries for CO2 trapping from this way, okay? Okay, now we measured calcium both ways, and then carbonates also in 2 ways, right? Okay, then you took all those total elemental concentrations of your solutions, and then you need to speciate to get ion activities. So we used a soil speciation model. This was developed when I was doing my PhD work at CSU. Then that program will give you different ion activities like calcium activity, carbonate activity, and CO2 partial pressure. Okay, this table, now we are in results and discussions. This table shows the total elemental concentrations of the solutions here. We got sample 1, 2, 3. Included here pH, calcium, magnesium, sodium, and we get total carbonates measured by two methods, direct titration and CO2 gas release method. We also included dissolved organic carbon in those soil solutions. Okay, we included 1, 2, 3 days of reaction, 1, 2, 3 day and 7-day of reaction time, and then units or negative log moles per liter there. Okay, pH, you can notice from these values, it's right around calcite equilibrium pH, okay, in equilibrium with atmospheric CO2. And the most thing here is, okay, as you increase the dissolved organic carbon, okay, the soil 1 had low dissolved organic carbon, and then soil 2 had medium dissolved organic carbon. When we go to soil 3, we had real high dissolved organic carbon, okay? The calcium concentration also increases as you increase the dissolved organic carbon in solutions when you measure with ICP. Similarly, direct titration method here also increases carbonates as you increase the dissolved organic carbon. This is true for all 1, 3, and 7 days. Okay? Then we plotted some correlations and see is there any relation between dissolved organic carbon versus carbon dioxide versus calcium measured by ICP, and also calcium, let's see, CO2 versus CO2 versus direct titration method, okay? Here we have DOC versus total calcium. We can see there's a pretty good relation between those two. That means at least it indicates that there is some relation between, as you increase the dissolved organic carbon, you also increase the total calcium in solutions. Here we plotted DOC versus total alkalinity, which is a direct titration method. It's also showed some relation there. We can't expand more on this, but at least it gives an indication that there is a relation between total alkalinity measured by direct titration method versus DOC here, similar to calcium. But when you have DOC versus CO2 gas release method alkalinity, there is no relation. You can see it's a flat line. Okay? Okay, this table shows the comparison between the activities measured by different methods. Again, we have 3 soils here. Then calcium activity from speciation of total calcium, which was measured by ICP, which includes both organics and inorganics. And then electrode calcium. Remember I said electrode calcium measures only inorganic calcium. No organics involved here. And then you got carbonate activity by direct titration method and CO2 gas release method. And then we got dissolved organic carbon also there. Okay, what we can see from here, as you increase the dissolved organic carbon, okay, let's see that. Let's take number 1. It has low dissolved organic carbon in soil. Then the difference between these two is not that great. Similarly, there is no difference here too. But if you increase the dissolved organic carbon, you can see the difference is getting bigger and bigger. So it shows some evidence that there is something going on with DOC there, okay? In this table, we presented ion activity products of calcite calculated from different calcium carbonate activities using. Okay, here we have reaction time, soil 1, 2, 3, and then we get mean 2. The first portion of the table shows the ion activity products calculated using calcium activity from speciation model, and then carbonate from direct titration method, which includes both organics and inorganics. And when you compare those ion activity product with the solubility product of calcite, which is minus 8.48, we can see these values are supersaturated. Means those values are higher than what you expect with equilibrium calcite. So these results suggest that soil solutions, those soil solutions are supersaturated. The second portion here, ion activities are very close to the solubility product, suggesting that they are in equilibrium with calcite, because we try to avoid the organics here in the second portion. That's why you see they are very close to solubility product. Okay, here we plotted log of calcium plus log CO2 versus pH for calcite solubility. This is calcite solubility isotherm right here. Okay? We included 1, 2, 3 soils, and also we used all 1, 3, and 7 days reaction time results here. Okay, the closed symbols were, again, includes your organics and inorganics, and then open symbols are just inorganic calcium and carbonate activities. You can see all those open symbols are very close to the calcite solubility line there, suggesting that those soil solutions are in equilibrium with the calcite. But if you compare these, they suggest they are not in equilibrium with calcite because they are supersaturated, higher than this line. And 7 days reaction period points fell right on the line. It's very close to equilibrium. Okay, then what I did is here, I took some literature values because there is a controversy about this one. And I took their values and then plotted on figure along with my results here. See, is there any relation, okay? What we have here is log ion activity product for calcite versus pH here. Okay, these are taken from storage. These are groundwater solutions, and then these are soil solutions right here. And then these are open and closed symbols are obtained in this study. Okay, these values and then these closed symbols are all used to measure calcium with the AA or ICP, and then direct titration of carbonate alkalinity. So these values, open, closed symbols, and then all these are included with organics and inorganics. And then whereas the open symbols are just inorganic calcium carbonate activities. So you can see these values suggesting equilibrium, whereas these are supersaturated. And fortunately, all these solutions here reported have very close organic matter what I had in my soil number 2. And then this is my soil number 3, had very close organic matter what these authors reported in their soils. Okay? And these ion activity products are very identical, very close to what they reported in the literature too. Okay, the possible explanation for this calcite supersaturation in soils at least is number 1, DOC, which is dissolved organic carbon in soils, complexes calcium, which leads to an overestimation of calcium activity because AA or ICP measures total soluble calcium, which includes both organic and inorganic calcium. Okay? Speciation models usually ignore these DOC complexes of calcium, so therefore you end up with overestimating calcium activity. Then second explanation is during the direct titration of soil solutions to determine the carbonates, DOC also, dissolved organic compounds will also absorb protons. So you end up with excess alkalinity. Therefore you get overestimation of carbonate activity too. Okay. Okay, there is a considerable evidence in the literature to suggest that DOC complexes calcium, and also it contributes to total alkalinity. Okay, there is some support in the literature, to convince, these results. So therefore, I put some references here. So we are not just pulling from the blue sky there. So it is possible that the dissolved organic carbon can complex calcium in soil solutions and also can contribute to the overestimation of alkalinity. Okay, the conclusions, I think almost. The mean log ion activity products obtained from calcium activity when electrode, from calcium activity with electrode and then carbonate activity with the CO2 gas release method ranged from minus 8.35 to 8.45. Those values are very close to equilibrium with calcite. And CO2 gas release method presented here is much better than direct titration method. That's it. Any questions, please? Go ahead and ask.
So let me take a stab at trying to summarize what you're saying here, that in fact, all the previous reports of supersaturation of calcite in solution in various natural waters have really been a indication of organic matter complexation of calcium rather than available inorganic calcium and carbonate species, which might affect equilibrium reactions with other trace elements and so forth.
Yeah, that's right. At least the results from this study suggest that calcium, dissolved organic carbon can complex calcium. If you don't take care of that, then you will end up with overestimating calcium as well as carbonate activities. Then you're actually, in fact, maybe you are in equilibrium with the calcite. So your assumption is you are not in equilibrium with calcite. That's what everybody thinks. So it has some implications on that. But this study mainly done on soils. We need to look into some lakes or river waters and so on, because they do have some organics, right? Dissolved organic carbon. So in that case, we might have some implication with that.
Could you not determine stability constants for your DOC calcium complex based upon your information?
Boy, you asked. That's a tremendous task. It's first thing is we need to know what kind of compounds we have, right? In order to measure any stability constants. That, I know, I think you are in that field, so you know how much difficult it is. It's very difficult to identify those compounds. Then once you identify those compounds, then you have to go back and then measure those constants. Then you can come up with exactly, like we are doing for inorganic complexes, you can include those complexes into your speciation model and then correct for organics too. But it's a kind of difficult task right now.
Well, based on your data, you know that you are getting complexation of calcium by DOC with one method, and the other method you're not. Mm-hmm. Could you not model these DOC calcium solubility or stability constants, put them back into your model to try and determine if they would hold? Theoretically, you could do it.
But it's a semi-quantitative type of stuff. Yeah, we can do that, but still, I feel it's better to know exactly what kind of compounds you have, and then it's very difficult. We can speculate. There is no problem. For nothing. Yeah. Indirectly, and then that's one of the things you're gonna do with me on this. So I think that's another approach. But still, it is difficult. If you don't know what kind of compounds you have, it makes it a little bit dark outside.
Could you comment on the implications of, say, modeling and predicting the solubility or availability of trace elements using a situation where calcite appears to be supersaturated as opposed to a situation where it's in equilibrium?
Okay. The best example is like phosphorus. We know there are some calcium phosphate compounds in soils particularly control or supposed to regulate this phosphorus availability to plants. But when you think calcite is not controlling the solubility of calcium, that means you end up with calcite, calcium phosphates also not controlling the solubility. So you might end up overestimating. Actually, maybe they are available to plants or something like that. Usually models, they are using a value, the one I showed with supersaturated 10 to the power minus 7.9. That's the value they use for calcite in those models. But actual value is 10 to the minus 8.48. So you might end up, overestimating or underestimating some of these nutrients or even elements which are environmentally, toxic. And also other good thing about calcite is if you know a system is in equilibrium with calcite, you can predict pH, you can predict other things too, trace elements like Glass was saying, you can predict other trace elements which are influenced by the calcite precipitation. It makes it easy for chemical modeling.
Any other questions? Thank you, Reddy.
Yeah, problem.